What we're going to do here is something called an optimization problem. Basically, it's a maximum or minimum problem. We're going to find the absolute maximum minimum of a word problem. And that's pretty important in the world because you want to find maximum profit or minimum amount of waste on making something. So there's a lot of applications of maxes and mims out there. So here's one situation. You want to make an open box from a square piece of cardboard by cutting equal squares from each corner and folding up the sides. Okay, you have a 6 by 6 inch piece of cardboard. What are the dimensions of an open box with the largest volume? So you want the largest volume made from this 6 by 6 inch piece of cardboard. Now it could be feet if that was the situation, which is kind of big. So inch is kind of a small piece of cardboard. We want the biggest size box I can make. Basically, the most volume with the least amount of surface area. That's what it's saying, or a given amount of surface area. Now you might have a little problem understanding what this problem was trying to say visually. So let me give you a little picture here. Sometimes optimization problems really help to draw a picture. Alright, so here we go. For the optimization problem, we have in this situation a cardboard, square piece of cardboard. And this square piece of cardboard is 6 inches by 6 inches. What it said is we're cutting out the corners. Alright, we're cutting the corners out, squares, and then we're going to fold on these dotted lines. Can you imagine when I cut out these corners and fold in dotted lines, can you see when I fold up this edge and all the edges, I have an open box on top. A box, if I taped up the corners, I have a box that I could put stuff in. Okay, now that is the situation. So how do we do this problem? How do we find the maximum amount of volume? Largest means maximum. So first thing I want to do is use the information we're given and make an equation to find the maximum of it. Now from this picture, hopefully you realize we're going to be cutting out x by x. We're going to cut out some length, but this is a square, so this length and this length are both x's. So all these are x by x, because in order to fold it, those have to be the same length. But we're trying to figure out how much we have to cut out basically to get the largest volume. Alright, so what are we trying to do? Find the largest volume, so we're maximizing volume. So my equation I'm dealing with is volume equals, well, of a box, isn't volume length times width times height. Well, yeah, length times width times height of a box is volume. Alright, so I'm trying to maximize this. Now if I try to derive this, it's not going to help me to find the absolute max because I have too many variables. I have V's, L's, W's, and H's. So I need to kind of shrink it down into more bite-sized pieces. So what I'm going to do is I'm going to think about this scenario. If I want my volume, I want to make, this is called my primary equation, and I'm going to fix up my primary equation to make it look better. I'm going to bring in secondary equations, separate pieces to make this better. So my length and width. Well, isn't my length and width just going to be these two sides? Isn't the bottom of the box length and width right there? If this whole thing is 6, well, wouldn't this length right here be the whole 6 minus x here and an x there? Because remember, don't I have an x here and an x there as well? Don't we have x's in all the corners? So isn't the whole thing 6 minus 2 x's? So aren't my length going to be the whole 6 minus 2 x's? And isn't my width going to be the same thing? 6 minus the 2 x's. So both these sides are going to be the whole thing minus the 2 x's. Now what's the height? Well, when I fold up these little flaps, aren't those heights just x? Do we now have a new function with all x's over here? Yes, we do. Each one of these individual pieces are called secondary equations. Secondary things to make your primary have fewer variables. That's the key. You got to make it have as few variables as possible so that you can actually take a maximum or minimum of the function. So that is very important. Draw a picture, visualize what's going on, and get as few variables as possible so when you derive it, take the derivative, you can find the absolute max. Alrighty, so let's make this equation easier to differentiate. I'm going to FOIL it all out. I just think that would be easier. So if we FOIL this out, we multiply those two, multiply these two, what I get is volume equals, looks like that would be 36. That right there would be negative 12x, and positive 4x squared. And I still have this x, which I'm going to have to multiply this x in to all that. Okay, when I multiply this x in, and I combine these, so if I bring this x in and combine them, I end up with 36x. Bring this in, remember these two together is negative 24x. If I bring that in, I get negative 24x squared. And that x comes in, multiplies by that, distributes in, I get 4x to the third. Alright, now I want to take the derivative or differentiate this so that I can find the relative max. This is mins, absolute max and mins in the end. Okay, so I want to take the derivative. So the derivative of v, okay, in respects to x, so you could write it as dv dx is equal to, you could also write v prime if you want to guess. The derivative of this is going to be 36 minus, well, 2 be negative 48x plus 12x squared. Alright, so what I now have, I'm going to rewrite this, make it a little bit easier to see, because I need to find critical numbers. To find absolute max and mins, I need to check endpoints and critical numbers. So if you think about this, your v prime, like a dv dx or just v prime, is equal to, well, I'm going to rewrite this to make it easier on myself to solve it. Do you see a GCF of 12 coming out of this? When I do that, I'm going to put x squared first. So I pull out the 12, I get x squared. When I pull out 12 out of here, I get negative 4x. When I pull out 12 out of that, I get 3. That's a whole lot easier to deal with. Now, can I set this piece equal to 0? So I got x squared minus 4x plus 3 equal to 0. Let's solve this. We're trying to find a relative extremis. So when I factor that, when you factor this, you will get x minus 3, x minus 1. If you factor that, which when you solve each of these, you get x equals 3 and 1. So these little pieces I'm cutting out, remember that's x, are either 3 or 1, or the edges. Remember, absolute maximum means you want to check edges. So I could also possibly check the edges are x equals 0 and 6. Those are the edges. Okay, now let's logically, before we go any farther, think of which ones make any sense. Alright, I cut out nothing. Well, if I cut out no edge, it's flat paper, I have no box. So let's say that's done. If I cut the whole 6 out, wait, how can you cut all 6 of it out? Okay, throw that one out, because I can't cut the whole, if this is 6, I can't cut the whole thing. Doesn't make some sense. Alright, if I cut 3 inches in, so if I go in and cut 3 inches, that's the middle. If I cut that in half, I can't fold anything. So that one's done. So you want to go through all your answers and see if it actually makes sense. So all I have left is 1. So is that my answer for x? Is that how I'm going to give you the maximum amount of volume? Well, it's asking for the dimensions, so if that's 1, it's asking, how do we know if this is actually the maximum though? Well, let's see if that's a relative max or min. That might help us out. How do you tell if that's a relative max or min? Well, we go to this. We take the second derivative. Watch this. If I find v double prime, okay, I'm going to call it x. You could put an x, by the way, dv dx, you get v prime, you can also put a v double prime x if you want, and leave the 12 out front. When you derive this, you get 2x minus 4, 3 disappears, alright, and then if I plug in 1, So what's v double prime 1? Well, that'd be a 12. That would be a 2 to be negative. So won't that be negative, which means, doesn't that mean it's concave down? Which doesn't mean it's a max. By the way, could I have done first derivative test to see if it's a max or min? Yeah, but I just thought I'd take a quick second derivative, plug in 1 to make sure it's a relative max. Because if it's a relative min, that's not going to help me at all, because that's going to be a low point. But now I know that's a relative max. All right. So all these other possibilities are kind of preposterous. So what I'm going to do is I'm going to assume that's my absolute maximum volume. And the question said, what are the dimensions? So if I cut out 1 out of each corner, okay, if this whole thing's 6, and I cut out 1, so what are the dimensions? If I draw my box, okay, if I drew, this is a 1, okay, all the sides are 1, all right, if I cut out 1 here and cut out 1 here, what's this left? Isn't it left with 4? Isn't that left with 4? Wouldn't it be a 1 by 4 by 4 box? Now how did I figure that out? Well, you go back up here and go 6 minus 2 times 1. Won't that give you 4, which gives you this length too? Aren't those the sides? You can do it that way, or you can kind of visually see it. So isn't this my answer? Aren't those the dimensions? A 4 by 4 by 1 box that's open on top? That would give me the maximum amount of volume with this given amount of cardboard. So if you were a business that was dealing with trying to save cardboard to make a package for something, it makes a difference on how much cardboard you use, because if you're making thousands of them, millions of them, you want to use as little cardboard as possible. So maximizing it is, the volume is pretty important. Okay. So when you do optimization problems, maximum minimum problems, okay, let's think about this again. You first want to get an equation, figure out what you're taking, the largest or smallest of. Then you got to make your equation so it has fewer variables, preferably just 1 over here. All right. Then you take the derivative of it, find your relative maxes and mins. All right. You want to think about edges. You want to think of other domain restrictions, because what happens when you find the edges and stuff, you realize that the edges don't make any sense. And then you want to verify, once you find that one value or more than one value, you want to verify it actually is a max or min, depending on what you're looking for. Second derivative test is very useful. You could also use first derivative test, whatever you want. And then once you get that, you then make sure you answer the question. So many people mess up. They might have given me the actual volume, because the volume here is actually 16, 1 times 4 times 4. But it asks for that. It asks for the dimensions of it, which is right here. So make sure you actually answer the problem. Good luck with optimization. Don't be scared of them. They're very useful maxes and min word problems.